So today it is my great pleasure to introduce our speaker, Robert Poole, who will be sharing his expertise in quality assurance in AI segmentation. And this is part of our ongoing machine learning seminar. So Robert is currently a clinical research fellow at the Inselgruppe and a PhD student at the University of Bern, where he is a member of the multimodal imaging and analysis group within the Auto Center for Biomedical Engineering Research. So, as I said, his research focuses on the validation and quality assurance of deep learning-based segmentation for brain and organ lesions. Robert previously worked as a technical physician in surgical innovation at the Netherlands Cancer Institute in Amsterdam, and continued his career as a clinical research scientist at the PSI Center for Proton Therapy, where he broadly focused on the development and implementation of new techniques in proton therapy. Robert then moved to the University of Bern for his PhD and has since published his work on AI segmentation and quality assurance in multiple international journals and conferences. Robert is also involved in the recently started CAIRO, the Center for AI in Radiation Oncology, and this is an arm of the umbrella of the Center for AI in Medicine. So we're very pleased to have Robert here today, and his talk will focus on AI quality assurance. Obviously, with the rapidly increasing use of AI in the medical field, ensuring consistent and reliable AI algorithms is something that will be crucial to patient safety. So we're very much looking forward to your talk today, Robert. And without further ado, I would like to hand over to you.
Yeah, so thanks a lot for this nice introduction, and welcome everybody that's here to hear me talk about the implementation of deep learning based auto-segmentation, which is in this case mainly focused on the radiotherapy application. And the subtitle already spoils a bit that the key here is quality assurance. So currently I'm involved in a Swiss funded project where we develop auto-segmentation models mainly for the brain on MRI. This is a collaboration between the Radiation Oncology Department at the Inselspital, the University of Bern, and Varian Medical Systems, which is one of the biggest vendors in radiotherapy equipment. And we are basically focusing on making models for organs at risk in the brain, glioblastomas, and brain metastasis. And within this work, I'm also doing my PhD on the topic of QA and implementation of these segmentation models. So most of the work I present will be focused on either organs at risk in the brain or on the glioblastomas. So, but let's start a bit from the beginning. So why do we want to have auto-segmentation in the first place? Well, in radiotherapy, full automatic segmentation has been one of the holy grails already for decades. And there's a good reason for this, because in radiotherapy, you need to have segmentations of your tumors so you can define targets, so you can treat patients. And you also have to define all the tissues that need to be spared. So this is mainly done manually, this contouring. So that means they have to do a lot of structures have to be contoured before treatment can take place. And the main issue is that this is, first of all, very time consuming, but it's also, it's inconsistent. So different raters, different institutions come up with different segmentations. And the idea is that auto-segmentation can basically solve both of these issues. So you have time gain and more consistent results. But the key here is, how can you do so while assuring the quality? So if we look back, so how can we determine if a segmentation is good or not? Most of the time, what we do is compare predicted segmentation against the ground truth. And this comparison can take place by different metrics, but the most important ones that you might know are the dissimilarity coefficient, which is basically a measure of the overlap of your prediction and the ground truth. And the next one is the Hausdorff distance. And this is basically the largest distance of your contour, of your predicted contour versus the ground truth cone. So first of all, we need to establish a benchmark, and so therefore we have to look at how the accuracy of manual segmentation is at the moment. And the benchmark we use is to look at what the inter-observer variability is. So how good can a physician mimic another segmentation? And the literature describes that in terms of the DICE metric, the inter-observer variability values for glioblastoma structures around 0.4 to 0.85, and for organs at risk, for the standard larger ones, DICE values can be quite high, up to 0.85, but for smaller organs, this is somewhat lower. So if we look at the accuracy in terms of the DICE, we can say it's around here, 0.8, 0.9. And this is definitely not perfect, but this is what has been accepted in the clinic up to date. So if we compare that against the accuracy of auto-segmentation, first we had atlas-based segmentation methods. After that, we got an upgrade with machine learning, but the current state of the art is all based on deep learning. And the literature, for instance, on organs at risk in head and neck, they have published DICE scores of well over 0.9 for most of the structures, some exceptions for smaller organs, but in general, we could say that the accuracy of deep learning lies here. And in terms of the DICE similarity coefficient, can say this is on par with the current clinical quality of manual segmentation. The question, however, is, will this be acceptable for in the clinic as well? And to answer that question, we also have to look at the other metric I introduced, the Hausdorff distance. And here we look at a result of the BRADS challenge, which was a challenge to segment the whole tumor. And we see here the results of all competing research groups, which have all a quite low results, which is supposed to be with a Hausdorff distance. It should be 0. But what's most prominent here is the outliers. And there are not only a lot of them, but they can also be quite severe. Some of the false segmentations are 10 to 15 centimeters away from the actual target. And these typical errors is also something we experience while developing our models. So at first hand, when we look at the results, they look quite good for the organs at risk and for the tumor as well. But what we also see is like typical errors that a human would never make. So here, for instance, we see some part of the pituitary is defined on the brainstem. We see some hippocampus here in the back of the brain. And also we can see that there's target segmentations on locations where there's no tumor resided at all. So this seems to be like an issue of robustness here. And this robustness issue and also the unpredictability of it, this impedes the implementation of such AI systems. First of all, errors of robots and therefore also AI are not really accepted in a clinic. And the unreliability of where these errors might occur, that makes that basically causes for manual checkups by physicians, and that again takes a lot of time for these physicians because they have to check the whole volume of the whole MRI because they don't know where this error might occur. On top of that, there's also no clear regulations on accountability. So if an AI model makes a mistake, no one knows who is responsible for that. And that further impedes the implementation. And this seems to be a problem for AI in medicine in general. And this is also reflected in a survey that was recently performed in Australia and New Zealand. And there they asked several physician groups if they think AI would improve their field of expertise, and about 75% they definitely think this is the case. But on the other hand, they also asked if they have used AI applications in their daily clinic, but over 80% have never used AI in their life. So there seems to be a mismatch here. So to sum up this introduction, there's we noticed actually three interesting things. First of all, we've seen that human contours can vary significantly in geometrical similarity, but this seems to be acceptable in the clinic so far. On the other hand, we have auto-segmentation models that can be on par with the human drawn contours, but it seems to be difficult to implement these into the clinic. What we also see is that the lack of robustness and the unpredictability might be one of the causes of this implementation problem. And this led us to ask several questions. First of all, are we using the right metrics to assess segmentations? And second, are these errors detrimental for the treatment quality? And then the final question is, so how can we solve this issue? But let's start with the first question. Are we using the right metrics? And to answer this, we came up with a hypothesis saying a metric will be good if it has any predictive value of the treatment quality. And to find out, we wanted to see if the metrics we currently use do correlate with treatment quality. So here we see the workflow of radiotherapy, and where we focus on is on the contouring part, and we have auto-segmentation models that then give us a prediction. And then if we want to compare them to a reference or a ground truth, we can do this by means of the metrics described earlier. And ideally, we want to see if there's a correlation between this metric and the treatment outcome. But unfortunately, treatment outcome data is not available and often takes quite some years to get. But besides that, we do have a direct correlation between the dose distribution and the treatment outcome. So instead, what we focused on is trying to see if there's a correlation between the metrics and the dose distribution for radiotherapy treatment. And the results are shown here. We see what we've done is like we plotted the differences we see in dose against the differences in two segmentation, but then defined in the specific metric, in this case, the dissimilarity coefficient. And what we expect to see is a trend along this red line, which is obviously not the case here for human rater alternative segmentations. So differences between different physicians. And also if we compare auto-segmentation results to the ground truth, there's no real correlation to be found. Actually, we did this analysis for all known metrics, and the result was basically that there's no correlation at all between any of the metrics and the dose effects that different segmentations would result in. So to come back to the question, are we using the right metrics? And the answer in terms of radiotherapy, you can say maybe not. So let's go ahead with the second question. Are these errors detrimental for the treatment quality? And to find out how often these errors occur, we developed a state-of-the-art deep learning model, which was trained on 100 glioblastoma cases. And this model was meant to segment the target volumes, mainly the GTV, which is the gross tumor volume, it's like the visible tumor, and the edema. And based on the results, we try to analyze how many outliers there are. So the image here shows you a graphic of how the model was trained, but there's no need to go into detail on that now. What is more interesting is the results. So here we see the numbers represent the amount of errors or outliers we found for each structure and for each trained model. But I can quickly make a summary of the results. Is that in half of the 100 cases, we saw basically these false positives. On average, more of 3 outlier volumes occur per case. And we also saw they have a significant size and they are of significant distance away from the actual target, which meant they can have basically an impact on the dosimetry and therefore on the treatment. And to check how much effect they have on the treatment, we did a dosimetric evaluation. So we took several predicted target volumes that have an outlier. We copied those and then removed the outlier part. And we also had a reference, a ground truth target that was defined by multiple physicians. And both the predicted with an outlier and the prediction where the outlier was removed had a dissimilarity coefficient of 0.17 with respect to this reference. And then we made a plan for all these 3 cases, which resulted in 3 different dose distributions. And from these 3 different dose distributions, we can then define what would be the clinical impact of the dose. And to do so, we looked at healthy brain. And healthy brain, in this case, is defined as all the brain tissue that is not defined as a target. And here the black curve represents the reference plan, and this is the ideal case where there's the least amount of dose going toward the healthy brain. And the red curve then here represents the case where the outlier was removed. And this difference here in dose is basically the dose effect based off the predicted contour. But we also see that here's the blue line that is represents the dose distribution where the outlier is still in place. So this particular dose effect is mainly caused by the outlier alone. So this means that these errors that occur can definitely have an impact on the dosimetry and thus the treatment. So these errors can definitely be detrimental for the treatment quality. So yes, and that brings us basically to our final questions. How can we solve the issue of impaired implementation? So to answer this question, we basically made a statement saying that the implementation of auto-segmentation can take place if the auto-segmentation can be effectively used without compromising the quality of the treatment. And to be a bit more specific with effectively, we mean it has to be significantly faster as manual contouring, and without compromising the quality, we define as it should lead to similar dose distributions. So the main goal here is to improve robustness and quality of the auto-segmentation models. And therefore, there's 2 approaches. The first one is to obtain better deep learning models. And the second is made to introduce checks and balances, so QA. And what we have seen so far is that the dose distribution is basically a good surrogate for the treatment quality. So what we are wondering is to see if we can use this dose distribution to improve the robustness and quality of these auto-segmentation models. So the first one is to obtain better deep learning models can be quite difficult. I think ever since the introduction of the modern UNets, there hasn't been much improvement in terms of accuracy of these segmentation models. You need to put a lot of effort in to get incremental increases. So this seems to be like a little bit of a dead-end street. So we basically focused first on trying to introduce checks and balances. And introducing checks and balances is something that takes place all the time, especially in workflows where humans are involved, and it's basically known that humans can make mistakes. And they even say making mistakes makes you human. And this is the same case with manual contouring. A human can make a mistake, and what you do then is to have it checked by another person. And it can even be have it checked by a group of persons if you want to get rid of even more mistakes. And this is basically known as the Swiss cheese model. So if you know that there can be mistakes, and you can introduce multiple layers that can filter out the mistakes so far that there are not any mistakes anywhere left. And this same principle you can also use with AI systems. AI systems are not perfect. So like humans, they can make a mistake. But in the same way, you can also have this checked by a different AI model. And if necessary, you can even use consecutive AI models on top of each other, like in the Swiss cheese model. So for our auto-segmentation models, we basically took this idea and tried to come up with a QA system that was based on two different independent deep learning models. And within this system, we don't want to look at the contour alone, but we also want to look at the probable effect that it might have on the treatment. So we use first an independent model to assess the contour prediction, and then a second model to determine the dosimetric impact. And both of these information can then be used to give feedback to the user for an efficient validation of the auto-segmentation results. So the first model we will use is a stochastic segmentation network. And this network is trained on different cases that have been manually contoured by different physicians. And with that, if you have the trained model and we introduce a new case, it can provide us with a probability map of where the model thinks the segmentation should be based on the manual contours of the experts where the model was trained on. So this will provide a foreground with a value of 1, where it's fairly certain that this belongs to this contour, the segmentation, and the background value at 0, where it's definitely sure this does not belong to the segmentation. And in between, there's a gradient. The second model we use is a deep learning model that can predict the 3-dimensional dose prediction. And these models are used a lot in the automation of treatment planning in radiotherapy. So there's a lot of literature around, and it basically comes down that you have a planning CT and your contours, which can be from your auto-segmentation model. And the model provides you with a 3-dimensional dose distribution prediction. Since we looked at glioblastoma cases, such a dose prediction model was not available yet. So based on some previous work from Babir et al., we trained our own model. And the results look like this. So on the left, we see a dose distribution that is planned and calculated on a treatment planning system. And in the middle, we see the prediction of our model. And here we see the difference between the two. So it's not 100% accurate, but it does give us a pretty good approximation of how much dose will be received by the different volumes, which at this point is more than enough for our QA model. So how does this QA model work then? So let's start off with our auto-segmentation model that provides us with a contour for our organ. And we can then use this as an input of the first contour variability model, and we get a measure of how valid this segmentation is or not. Then the probability map can also provide us with a worst case over segmentation and a worst case under segmentation that is realistic. And these can both be put into the prediction model, dose prediction model, and that can provide us with a measure of what the impact might be on the dose. So in more detail, that works like the following. Let's say this is your outcome of your auto-segmentation model, your contour. You can overlay this on your probability map of the first model, which can give you a measure of the contour validity. Then you can take your segmentation and use it as input for the dose prediction model, and then it can calculate how much dose will be received by the volume. You can get like an over-segmentation, worst case scenario from the probability map, and also as it as an input of your dose prediction model, and then we'll provide you with a different dose received. In the same way, you can also do this for a worst case under segmentation. And this also can be put into your dose prediction model and provides you a new DVH. And then this particular difference between the two worst case scenario can provide you with a measure of what the possible dose effects might be for this particular, or in this particular case. So together, these measure of validity and the dosimetric impact can basically give you information to accept or reject a contour. So instead that after your auto-segmentation, you have to manually check each and every contour. This QA model will provide you with the specific contours that are fine and will not have any impact on the treatment. And it points out specifically which contours used he thinks needs additional checkup. So this can be a lot of help. So the physician that uses this is more secure that there's no errors anymore. And if there are errors, it's pointed towards where these errors might be. So it makes it much more effective. But we can even go a step further. A colleague of mine, Amit Kamat, and together with some colleagues of the Department of Radiation Oncology in Zurich, they set up a study called AquaRT, which is also into quality assurance of organs at risk delineation. And what they did is they used the same dose predictor and basically on the surface of auto-segmented contours or manually segmented contours, they added spherical blobs, and they used the dose predictor to see what the effect then would be on the dosimetry. And they did these spherical blobs everywhere on the surface of an organ and calculated the dose predictor over and over again. And what you can get eventually is basically, here in red we see the target, and this is the brainstem. And what we have here is a surface map that points out what particular parts of the surface, if you change them, would have the most impact on the dosimetry. So you're not only being pointed in the right direction of which contours you should check, but also within the contour, it points out what the most critical parts are to evaluate. So then we need to go a little bit back to this slide. And so we now have basically focused on inserting checks and balances. But we also wanted to see if with this dose predictor, we could maybe obtain some improvement in the deep learning models. So basically, see if we can go into this dead-end street anyway. And a colleague of mine, Elias Rüfenacht, he's developing currently a auto-segmentation model for glioblastomas. And what he did, he also used this dose predictor model, and he tried to incorporate it into the loss function. And what this basically does is it will penalize false segmentations more if they have a higher impact on the dosimetry. And the first results of this model, we did some dosimetric evaluations. So we basically evaluated on the final dose distribution. And what we saw is that basically with this dose loss method, it can provide dose distributions that are closer to the actual planned ground truth than what you can get with a standard loss function using, for instance, binary cross entropy dose loss. So this is a very interesting finding, and still quite preliminary results, but it's interesting to look further into if we can leverage this into improving deep learning models, or at least make them more robust. So then what last me is to provide you with some take-home message and what is the most important things that we should remember. And I try to keep it a little bit broad and general for implementation of AI in medicine. So first of all, I think what is important is AI models can check other AI models. So the models are not always perfect, but within a Swiss cheese model, basically what we can do is assure the quality of imperfect AI. And the second thing is to look at the broader picture. So in the case I described now, where we want to make auto-segmentation models for radiotherapy, we don't really want to focus on the specific application at hand, but look at the broader picture and see what information is there in the total workflow that can make your application basically more clinically relevant. So with that, I would like to thank you for your attention, and I will be glad to take any questions.
Fantastic. Thank you very much, Robert, for that incredibly interesting talk. I'm sure there will be a lot of questions from the audience. Just before we get to that, just a reminder, if you would like SSR credits for this talk, please drop your email in the chat. Great. So I'd like to open it up to any questions from the audience, and please feel free to also write in the chat if you have a question.
I have a question, Katrin. Thank you, Robert. It was really impressive. I never saw such an approach for the quality control. I think one point you didn't mention, or maybe I've missed. What about the qualification of the specialists which are providing the ground truth? Did you consider that people have different experience or may have also a different risk affinity when they are providing their annotation? Does it play a role in the final assessment of the quality of performances of your algorithm?
Yeah, so this is an interesting question, because we're also always referring to a ground truth, but basically there is no real ground truth, right? Mm-hmm. So there's a lot of say like discrepancy in what you can see on an image. So, but basically how we try to solve this issue is we don't let one physician make a ground truth. We it's basically a consensus of 3 experts. So one expert starts with contouring, then the second adjusts accordingly, the third evaluates that, and then on every case where they do not really agree, they discuss to come to an agreement. So this is one way where we try to get as close as possible to a ground truth. But indeed, there's a lot of difference in here, and there's even differences in definitions of different guidelines for this. So this is also one of the issues where we run into while developing these models, is as long as there's no consensus among how a specific contour should look like, then an auto-segmentation cannot provide a perfect model for everyone. So.
I agree.
And just maybe to follow up on that, on Christina's question, if you have models that tend to check your first model, is there also an approach where you just have multiple models that do the segmentation from the start, like redundant systems, and then you kind of have a weighted average of which models give you the closest outcomes to each other, like you'd have with the physicians? You have 3 physicians and you kind of see where they agree. Is that also an approach that's being taken?
Yes, like maybe I have one slide here I can show. Like this is, for instance, it's quite standard that they now do ensembling training. So basically what you do is you train, based on your data, you train 5 different models with different split sets of your data. And in the end, what you do is basically do like a kind of a majority vote of the outcome of the 5 different models, which makes your outcome definitely more robust than it was before. The problem here is a bit that these 5 models that you make, they're not independent from each other. They use the same network, they based on the same data, so they can make the same mistakes. And so the key point also is, when do you do QA with different AI models, is that you have independent models. And preferably, they're complementary to each other. So if one model flaws in one direction, you need to have a QA model on the other hand that is quite strong in that direction. And this is also why we introduced additional information, for instance, in the QA model, like the dose distribution that is not there in the initial model. So it definitely provides new information that was not there before. So they complement each other. Is that an answer to the question?
Yes, definitely. And I guess another follow-up to that, if no one else wants to jump in, do you ultimately see that they will also incorporate clinical outcomes into these models? So with this kind of independent data set that you're talking about with dose distribution, like as we get more data in this age of AI, do you think that we will eventually kind of incorporate the long-term clinical outcomes? Do you think that would be beneficial? Do you think it's somewhere where the field is going? Or yeah, what are your thoughts on that?
Well, that would be the ideal case, right? That you can test models all the way up to clinical outcome, but I don't see that happening very fast. Mainly because it costs a lot of time and money to set up studies like that, and there's ethical considerations that probably are withholding us from doing studies like this. But I think in the end, if models are implemented, you would get constant evaluation, and you will eventually can also make evaluations on clinical outcome and see retrospectively if a model has indeed had an impact on improving the outcome, or at least did not had a detrimental effect on the clinical outcome.
I have a question on that. What about considering that information you may know in advance? So, for example, not only the imaging features, but also some characteristics of the patient that may bring a specialist to be more generous on the segmentation rather than more restrictive on the area to treat. This should not be so far away from the clinical reality, but did you make some attempts there to include this information in the segmentation?
Yeah, so our belief is basically that AI can assist, but it will never take the full task away. So first of all, the physician will always check up and have their personal input based on specific case. So it can always adapt contours to the needs to the clinical needs of that specific patient. So we will definitely not make auto-segmentation models that cut out the role of the physician all the way. I don't think that's possible anyway. So, but it's merely AI models can assist in all the laborious work, and let's say 80–90% of the cases could be easily done. But for this 10% that are outliers, yeah, there's like input of the physician required, and I don't think that will change very fast.
Great. I think we have time for maybe one more question, if anyone from the audience has, and if not, I will end on a more broad question, which is basically, how do you see us integrating these quality assurance metrics or models into regulations? So how can we use this in regulations to make sure that AI globally is safer and that clinicians trust it, and kind of so that it enhances uptake of AI methods in hospitals? Because I think a lot of hesitation is on patient safety, and if there was something about quality assurance within regulatory frameworks, I think that might help. So what do you think? Are we making progress on that front? And yeah, do you see us integrating quality assurance models into regulation in the future?
So there's multiple aspects on why this implementation is difficult. And I think the main two topics is, first of all, the trust of the users into the systems. First of all, it's a black box, so they cannot really validate often. But the second issue is, especially with auto-segmentation, is they can obviously see it makes mistakes. And that's why they don't trust it anymore. And that issue, I think, can be solved with QA. So if you use QA and you basically don't say, oh, we can make 100% accurate segmentation, but we can make auto-segmentations, and we have QAs in place, and we can assure you that 80% of them will be all fine, but we still need you to check maybe 20%. I think that's a statement that is realistic. And if you can basically show to the end users that you can make this true, they will get trust in the system. As for the other issue, is basically has to do with the accountability, I guess. And I think my opinion is that this accountability should be regulated from the top down. So governmental bodies first, and they have to put rules upon vendors, hospitals, or users, or physicians. Because at the point is, what is now is that, yeah, people have to take responsibility themselves, and no one is really, or everybody's a bit wary to do that, right? Because it's not really sure what the consequences will be eventually. And in that sense, I don't really see a lot of improvement, but you do see a lot of papers coming passing by on getting frameworks for this and how to solve these issues. So yeah, hopefully it will get
one day soon.
forward. Yeah, it is. Yeah.
Great. Well, I think we've reached our time limits. So I'd just like to say thank you very much again, Robert, for the fantastic talk. And also to remind everybody that our next machine learning seminar will be on the 20th of July. So that will be on synthetic CT from MRI images for radiotherapy planning. So yeah, thank you very much for attending. Once again, please leave your email in the chat. And thank you, Robert, for a fantastic talk.
It was a pleasure. Thank you all for listening.